Hi everyone. So in the last video we explored Markov chains and how they help us model state transitions. So now we are going to add a key component to our framework, rewards. So this will bring us, take us to Markov Reward Processes, really an important step in understanding Markov decision processes and ultimately reinforcement learning. Okay, so today will be on Markov Reward Processes. So mathematically speaking, this is a tuple of states, a set of states, probability matrix. If you remember, this was the Markov chain, but the Markov reward process has an extra signal, a reward signal, and a gamma, which we are going to take a look at later on. Okay, so this on its own, this is the Markov chain. Today we are adding the reward signal and the gamma. All right, so let me show you the system that we are going to be working with. We are going to be working with this, with this 2D cleaning agent. We have seen the 1D cleaning agent, which could actually move left or right, but this 2D system, the agent can move down, it can go left. So we have 4 states here. This is the charging station, this is a dustbin, and the agent's goal is to pick up trash to the dustbin. And sorry, I have also denoted a small t here. I'm not sure if you can see it, and also a small t here to denote that these are terminal states. Okay, now we are talking about rewards. What we are going to do is, but before then, let me give you this is the, maybe I can put it here. This is our probability matrix. Okay, so we have 4 states. This is the probability matrix and the reward. Well, the reward of S0 is going to be 5. Reward of S1 is going to be 0. S2 will be 0 and S3 will be 10. What this means is, when I get into, for example, S0, I'm going to receive the agent. When it gets to state of 0, it's going to receive a reward of 5. When it gets to this state, S3 is going to receive a reward of 10. These 2 states do not have any reward. So this is the reward that we are talking about. Really, think of it as a short-term success, as a short-term feedback. The agent does something, moves to a state, and it receives a feedback. Now, in reinforcement learning, we are not just interested in immediate rewards, these ones. Long-term success is also important. And this is where the concept of return comes in. Now think of return as a more like accumulation of rewards in an episode. We have already seen episodes. So return represents a cumulative reward an agent expects to receive over time. We are going to start with, maybe I can divide this. I think we have a space management problem here. I'm going to start with a finite horizon return. A finite horizon return, which essentially is a summation of all the rewards that agent gets in an episode. So it's going to be something like this. Return is usually denoted with the letter G. In literature and in reinforcement learning books, the return sometimes is known as a gain. So that is why it's usually denoted with letter G. We are going to denote it from time t to time big T is going to be the summation from, let's say k is 0 all the way to t minus 1 big T, and the reward that I will get from t plus k plus 1. Okay, now maybe I can give you a short example. Let's see. Example. Okay, now imagine this t is a parameter. I mean, what we are doing now is computer returns, long-term success. Okay, so this t is a parameter. It depends on your application. We can make it to be, let's say, 3. And depending on where the agent is, maybe the agent is currently in S1, we can compute the return. So let me say that this is a sample. Let's create a sample episode. Okay, well, a sample episode can be something like this. The agent is state 1, S1. From S1, maybe it can go to, let's say, S2. From S2, then it can go to S3. Okay, now let's compute the return for this particular episode. From S1 it goes to S2. Well, S2 has a reward of 0, so it's going to be 0 plus. From S2 it goes to S3. S3 has a reward of 10, and then since S3 is a terminal state, we stop. But we are looking at 3 times steps ahead, so we're going to add an extra 0 just to make it 3. This is going to be 10. So for this particular episode, the return is 10. Let me give you another example. The agent is in state 1. From state 1, it can just go to state 3, and then it ends. State 3 is a terminal state. Well, from state 1, it goes to state 3. It receives a reward of 10. Since t is 3, we are going to add multiple zeros to get 10. Okay, I hope you get the idea. Let me give you one final example to get the point of this t, big T. This is a sample episode. Maybe the agent can be in state 1. From state 1, it can go to state 2. Right? From state 2, it can go back to state 1. Then state 2 again. Then state 3. From state 2, it can go to state 3, for example. Well, from state 1 to state 2, going to state 2, it receives 0. Going back to state 1 plus 0. Going back to state 2 plus 0, reward of 0. State 2 to state 3 is 10. But remember, t is 3. All we care is the next 3 time steps. So we are just going to take the first 3. That's all we care about. And the return is going to be 0. Now think of it. Think of this. The problem is that depending on t, we can end up with different returns. What we can do is we can go back to this formula, find a state horizon return, and make it an infinite horizon return. So I'm going to cancel this t and make it infinity, and then cancel this to infinity, which means that we are just going to be summing all the values, all the returns. So here it's going to be the same, it's going to be the same. However, here it's going to be 10. So this is it has changed from a finite horizon return to an infinite horizon return. Okay, so now we have more like made an improvement. Well, we can go one step further. We are currently in the infinite horizon return. The challenge we now face is assigning different levels of importance to different future states. So we have multiple future states here. We want a way to give different importance to further states. I mean, states that are way ahead compared to the immediate states. Okay, so another problem is that summing these values, many different rewards, can lead to unbounded results if we have like a lot of states, which can make the problem mathematically unstable. So what we're going to do is introduce a discount factor gamma, which is this, okay, this gamma. This parameter, helps us weigh the importance of immediate rewards more heavily than distant ones, so allowing us to really stabilize learning and ensure convergence. And this value is typically between 0 and 1. Okay, so we are introducing gamma, which is between 0 and 1. We are going to see an example. So now we are going to have, sorry, I have our 2D cleaning agent. We don't want to ruin it. What we are going to do is introduce a new return formula. Well, this formula is going to be like this: return, sometimes gain. In reinforcement learning books, it's going to be something like this: summation, let's say k from 0 all the way to infinity of gamma to the power k times r t plus k plus 1, which is essentially the first reward that we receive, t plus 1 in the next state, plus gamma rt plus 2 plus gamma to the power 2 r t plus 3. Okay, so notice that from the next state we start discounting. Sorry, so we go to the next state, we get an immediate reward. We go to a next state after that, then we start discounting. Okay, so this really are discounted. Now think of this: depending on gamma, when gamma is close to 0, we are going to be emphasizing on immediate rewards. So imagine if gamma was 0, these values, these highlighted values, are really going to go to 0, and we are only going to give importance to the immediate reward. When the gamma is high, long-term rewards are given importance. So the higher it is, the more importance we give to future states, future rewards. So this balance allows us to control how much importance we assign to the future rewards versus the present ones. Okay, now it doesn't stop there. You see, we started with the finite horizon return, then the infinite horizon return, which also had its problem. Now we are in this particular return formula. Okay, now what we are going to do is to introduce a value function from this return formula. So we are going into value functions, which is really, I think, a major step. And I'm going to denote this as approach. Okay, so from this I'm going to get a value function, which is going to be something like this. The value, okay, maybe before I write the formula, it's important to tell you what it is. The value function tells us how good a state is based on future rewards we expect to collect. So this is really a fundamental step in understanding the agent decisions, as it provides a way to compare and prioritize states based on their long-term potential. So different states can have different values. Okay, essentially telling us how good a particular state is. So we have, let's say we have this particular state S. To compute the how good it is, we are going to say from K, starting from 0 all the way to infinity, gamma, oh, by the way, this is not Y, this is gamma, sorry. This is not Y, this is a gamma, R K plus 1. Given that we start, the initial state is S, okay? I think I have a problem with this pen. Then what we are going to do, since we have a probability matrix, I'm going to add an expectation. I am just really just introducing this value function, but we are going to go in depth into it because we needed to get the Bellman equation. I'm just really introducing it for this video, but in the next video we are going to break it down to see what it is. It has an expectation here, for example. Okay, so the value function, you just have to know that it gives us how good a particular state is. However, I'm going to show you another way to get the value of a particular state using an empirical approach, using sampling. Okay, empirical approach. Let's say sampling. Let's say, sorry, this is sample based. I'm going to call it sample based learning. I hope my handwriting is not a problem here. Okay, so this is an analytical, more like the absolute way to get the value of a state, but there's another method. What we are going to do is, let's compute the value of this S1, okay, V S1.
It's 5 o'clock.
So the S0, what we are going to start with, is going to be S1, and I'm going to denote gamma to be 1/2. And this method is just going to use this formula, but without this expectation. What we are going to do is, from this particular S1 state, we are going to sample some episodes. Okay, so let's say a sample episode could be from S1, it can go to S2. Then from S2 it can go to S3, and S3 is a terminal state, then we stop. Okay, so what is the return here? The return, we have actually computed it, but let's see. Anyway, the return is going to be we are actually going to be using this formula. You know, I actually forgot to give you an example for this particular formula. I think I skipped it. But before we go to this particular empirical approach, let's calculate a simple return, which is essentially what we are going to be doing here. So a sample episode, so I'm going back here, I'm stopping what we are doing here. I missed a step. A sample episode could be, you know, S1, sorry, S1 to S2 to S3. Using this formula, the return is going to be, well, from S1 I go to S2, I receive a return of reward of 0. S2 has a reward of 0. From S2 I go to S3. Sorry, there's going to be an addition here. Well, S3 has a reward of 10. But don't forget, this S3 is going to be discounted by gamma. And gamma, we can denote it, we can use this gamma 1 over 2, right? Over 2 times 1 over 2, the same thing, as going to be 5. So using this return formula, this is what we have gotten for this sample episode. Okay, so I am really just giving an example here, and this is actually what we are going to be doing here. From S1 to S2 to S3, we are S2 is 0, S3. Okay, we have a problem here. Okay, sorry for that. See plug here, I'm going to use this. Okay, S2 is 0, S3 is 10. But with the future reward, is going to be discounted by 1 over 2 times 1 over 2. This is 5. Similarly to what we have done here. Another sample episode. So what we are doing is sampling episodes, but from episode that start from S1. Our goal is to compute the value of S1. Okay, a sample episode could be S1, let's say to S3. Essentially what we did here, but with discounting. Well, from S1 I go to S3, I get a 10, a reward of 10. But there isn't going to be a discount, because it is the most similar, it is the most immediate reward I get. Another sample episode is going to be from S1 I go to S2. From S2 I go back to S1, then to S3, sorry, S2, then to S3. Okay, now from S1 to S2 I get a reward of 0. Okay, immediate reward of 0. From S1 to from S2 to S1 I get an immediate reward of 0, right, but discounted. Then plus, from S1 I go to S2. Well, S2 also has a reward of 0, but it's also going to be discounted by 1 over 2, but this time to the power 2. Okay, plus from S2 I go to S3. S3 has a reward of 10, but it's also going to be discounted by 1 over 2 to the power 3. Okay, now all of these values all of this are 0. I mean, they have multiplications by 0 are going to be 0. Now this is going to be just 10 over 8. Okay, now we're going to do for this sample episode, we are going to add this 0, 5 plus 10 plus this, then divide by 3, because we have 3 episodes. We are going to stop here. We are going to be sampling 3 episodes. Okay, 5 plus 10 over 3, all over 3, and you are going to get something like 5.4, I believe. Okay, so the value of S1 is going to be 5 over 4, but of course using sampling, the more episodes you sample, the more accurate this value is going to be. Again, I'm just giving you a way to compute values, but this is the absolute way that we are going to be seeing in the next video. Okay, I hope this is clear. So what we did, we started the finite horizon return. I gave you this example, but we said the finite horizon return has a problem of this big T. Then we moved it to infinite horizon return. We replaced T with an infinity, this with infinity, but it also had problems that we do not discount future rewards. And then I introduced formula. I gave you this example to compute the reward using this particular formula that has some discounting. Then we move to the value function, which I gave you, that we are going to be looking at again in the next video. Then we look at another an approach to compute the value of a state using an empirical approach, sampling based learning, where we, for a particular state that we want to compute the value of, we sample many different episodes that start with that particular state, get their return using this formula, and then taking the average as we have done here. Okay, I hope this is really clear. Let me know if you have a question in the comments. Okay, so now we have understood the Markov reward processes, right? We have seen the Markov reward processes, really a Markov chamber with more signals. In the next video, we are going to build upon this to get the Bellman equation. I am also going to give you an example to get the value of a state using this particular formula, where we are going to be leveraging the probability matrix, because this probability matrix provides an absolute, more like the absolute, I mean, a sense. It's going to be useful in essence to compute the absolute value of a state. And then from there, we are going to be introducing the Markov decision processes, where we're going to start seeing actions, agent moving left or right, which is essentially this, but with an action signal. Okay, I hope this is very clear. There's going to be a Jupyter notebook related to this particular video that you can play with. Again, if you have any question, please do not hesitate. Let me know in the comments. I'll try my as much as possible to answer your question. All right, thank you very much.